So we've looked at how to multiply two vectors to get a scalar. That was a scalar or dot product. And now we look at another way of multiplying two vectors together to get another vector. And this is the vector product, or the cross product. We write the cross product as A cross B. And it's defined as the magnitude of A times the magnitude of B times the sine of the angle between them times a unit vector n. So for the dot product we had the cosine of the angle between them. This time we have the sine of the angle between them. And we also have a unit vector that gives direction to this vector. So the question is, in what direction should this unit vector point? And the answer is that it must be perpendicular to both A and B. If A was in this direction, like the x direction, and B was in this direction, the y direction, A cross B will be coming straight out of the page. So I can't even really draw it here. But it will be pointing straight out at you in this case. In an x, y and z coordinates, if A was in the x direction and B was in the y direction, A cross B will be in the z direction, coming straight out of the page. So the vector cross product is a thing in 3 dimensions. Because if you have two vectors in the plane and you want another vector that's perpendicular to them both, well, that has to be coming out of the page in 3 dimensions. In order to remember the direction of the cross product, you can use the right hand rule. So if you're finding the cross product of A and B, if you point your index finger in the direction of A and your second finger in the direction of B, like the picture, then your thumb is pointing in the direction of A cross B on your right hand. So the direction of this new vector n, the unit vector, is in the direction of your thumb, and hence the direction of A cross B is in the direction of your thumb. So that's a rule to remember the direction of the cross product. So now let's do like we did for the dot product and take two vectors A and B broken up into their components, A1, A2 and A3, in the I, J and K or X, Y and Z directions. So if we write that out, we have A1 times I plus A2 times J plus A3 times K times B1I, B2J, B3K. And if we multiply all that out, we get this big long thing. This big long awkward looking thing. So let's look at the different kinds of terms that we have. So the first term here is A1, B1, I cross I. Let's take a quick look back at the unit circle. So this is a circle of radius 1. In X and Y. And if you think back to your definitions of sine and cosine, the length of this is 1. If we have some angle down here, let's call it theta. This side up here, the blue side, is going to be sine of theta, and that green side is going to be cosine of theta. Because remember that sine is the opposite over the hypotenuse and cosine is the adjacent side over the hypotenuse. The hypotenuse here is 1, so that green side is just cosine of theta, and that blue side is just sine of theta. So this unit circle thing is just a quick way to figure out what sine and cosine should be, if you can't remember. So in this case, we have AB times sine of theta. So when that angle between your two vectors, theta, when that's 0, you can see that sine of theta is going to be 0. And when that angle is at 90 degrees, then sine of theta is going to be 1. So that's that blue side of the triangle. So when that yellow angle goes down to 0, that blue side goes to 0. And when that yellow angle goes up to 90 degrees, that blue side becomes 1. So let's apply that to I cross I. Well, I is in the same direction as itself, obviously, So that angle is 0. When the angle is 0, then sine is 0. So I cross I, or j cross j, or k cross k, because the angle is 0, all have a cross product of 0. And let's not even worry about the direction. It's 0 times some unit vector. But since it's 0, it doesn't really have a direction, so forget about it. So all those terms are basically gone. All 0. I, j, k. So the next thing we want to worry about is what's I cross j, j cross k, and k cross I. Well, these angles between them are all 90 degrees. Between any pair of them is 90 degrees. So sine of theta is going to be 1. And the lengths of the two are also going to be 1. So the length of any of these vectors is going to be 1. But the question is, what direction does it point in? Or what is the appropriate unit vector to use here to give it direction? So apply your right hand rule. So I, j and k look like this. If I is in the x direction and j is in the y direction, then k is pointing straight out of the page at us. So apply your right hand rule to that. Put your index finger along the direction of I there in red, and your next finger in the blue in direction of j, and you'll see that your thumb is pointing straight up in the direction of k. So I cross j is just 1 times k. So I cross j is equal to k. What about j cross k? I'll do the same thing. If you can twist your hand so that your index finger points in the direction of j, your next finger points straight up in the direction of k, you'll see that your thumb now is pointing in the direction of I. So j cross k is equal to y. Do the same thing for k cross I, and you'll see that you just get j. So now we have I cross j. What about j cross I? Is it the same? Well, go back to the right hand rule there for a cross b. If you look up here and you put your index finger in the direction of b, because that's going to be the first one, and your second finger in the direction of a, because we're getting b cross a now, you'll find that your thumb is pointing straight down into the page. So a cross b was pointing straight up, b cross a is pointing straight down. So the general rule is that b cross a is equal to minus a cross b, because of course minus a vector is the vector pointing directly in the opposite direction. So we have I cross j. J cross I will be equal to minus k. K cross j will be equal to minus I, and I cross k will be equal to minus j. That's taken directly from these three by just changing the sign, because I've swapped around my two vectors in the cross product. So now I have everything I need to work out that big long thing up here. So I can sub in all those values and we'll see what I get. And what I get is this. This is where I've just subbed in the values. And then you see that some of them are 0, there's some minuses and stuff in there. So if I take out a factor of I, j and k where I can, and I sort out all the zeros and pluses and minuses, I end up with this. So that's quite a bit more complicated looking than the dot product. But the easiest way to remember it is that if you look at it, you'll find that it's actually the same as this determinant. So if you write down I, j, k in the first row, A1, A2, A3 in the second row, B1, B2, B3 in the third row, and calculate that determinant, you'll actually get that expression for the cross product above. You'll see that if I expand along the first row, so my first term would be I times plus I there, right, times the determinant of what's left, A2, A3, B2, B3. and then it would be minus j times the determinant of a1, a3, b1, b3, and then it would be plus k times the determinant of a1, a2, b1, b2. And you'll see that when I work that out, I'll get back that formula above. So here's your a2 times b3, and here's your minus b2 times a3. And the same with your three terms. So you don't have to remember that formula on top. If you want to remember how to calculate the cross product in terms of the components of a vector and I, j and k, you just have to remember this matrix and remember that it's that determinant that gives you the cross product. So it's your three ijk's on top, then your a's, and then your b's, which is much easier to remember. So now let's look at some properties of the vector product. The first one we've seen already, which is that a cross b is equal to minus b cross a. The second one is how to do with multiplying a scalar in. So if I multiply a scalar in front of the whole cross product, that's the same as multiplying that same number in front of a or in front of b. The next one has to do with how the cross product distributes over addition. So here I have a cross b plus c. And you can see that's the same thing as doing two cross products, a cross b and a cross c, and adding them together. So in that way it's just like regular multiplication. If you had regular numbers and you had a times b plus c, that would be equal to ab plus ac. So the cross product works a lot like that. Also, if you have here, we have a plus b cross c, it works the same way on the other side. So whether the cross product is on the left or the right of the addition, that still works. The final property is putting two cross products together. So here we have a cross b cross c in brackets. Now this is important, that is not equal to a cross b cross c with the brackets over the a and b. So if you have two cross products together like that with one in brackets, you can't put the brackets wherever you like, or you can't do it in any order. So that's different from normal multiplication. Normally if I have numbers a, b and c, and I have a times b times c, that's the same as a times b times c, like this, with regular scalars. But for the cross product, that's not true. And a cross b cross c is not equal to a cross b and cross c afterwards. So that's one to remember. And then our final property is one that we just discussed, how to calculate the cross product from components. And it turns out to be this determinant. Your unit vectors on top, your a components in the second row, and your b components in the third row. Now let's look at a geometrical interpretation for a vector product. So we start with a parallelogram a, b, c, d, and two vectors, the vector from a to b and the vector from a to d. And we're going to look at the cross product of those two vectors. So for any two vectors that are making a cross product, you can construct a parallelogram around them like this. This parallelogram has height h, which is this length, and the area of the parallelogram is that height h times the length of AB. Now we'll work out h in terms of the cross product AB and AD, and we'll get the area in terms of the cross product. So if I put in that angle theta, sine theta is the opposite over the adjacent for this right angle triangle. So that's h over AD, the length AD. So I solve that and I get that h is equal to the length of AD times the sine of theta. So my area now is h times the length of AB, which is just AB times AD times sine theta, or those lengths. So if you look at this thing here, AB, AD, sine theta, which is the angle between them, that's nothing but the cross product, or at least the length of the cross product. So that's the cross product without the unit vector part. So it's just a scalar, but it is the length of that cross product, or the magnitude of that cross product. So the area of that parallelogram is the magnitude of the cross product between AB and AD. So that's a geometrical interpretation of the cross product. The magnitude of the cross product is the area of the parallelogram built by the two vectors in the way shown in that diagram. Or you could think of it as the area of the triangle. So if you look at that triangle made by ABAD and the line from B to D, you can see that the area of that triangle is just half that. So that's another way of thinking about it geometrically. It's the area of the parallelogram, or it's half the area of the triangle. And when you think about it like that, you can see that when the two vectors are pointing in the same direction, that area goes to 0. So if I have two vectors very close together like this, you can see that that area is going to be very small of that little parallelogram. But if they're the same length, but they're kind of pointing totally opposite directions, well, now I get something that's a square. That's the biggest that area can possibly be. So where the dot product was kind of measuring how much the two vectors are pointing in the same direction, the cross product is biggest when the two vectors are at right angles to each other, whereas in that case the dot product is 0. So that is the cross product, or the vector product. So now that we have the dot product and the cross product, we can finally start looking at where they're actually going to be useful. So that'll be coming next.